Okay, we're going to continue our discussion with Simulink Matlab tutorial, and here we're going to, in this case, we're going to do a low pass filter. So let's do a quick review. So here we have a transfer function, output over input, described by this h of s, and we call that the transfer function. And we used a simple RC circuit to implement this low pass filter. And it turns out that the equation will be 1 over RC S plus 1 over RC, which is like the Laplace domain description for this input-output relationship. S is a complex number, and for sinusoidal signals, sines are cosine inputs. Then we have S can be approximated with j omega, and when we do that, we have this relationship, and we can see that this is just a complex number. Here in the numerator is just the real part, and in the denominator we have a real part and imaginary part, or simply a complex number. So finding the magnitude in the numerator is just 1 over RC, and to find the magnitude of the denominator we follow the standard process of squaring the real part, square the imaginary part, and then taking the square root of them after we add these two numbers. And then the corresponding angle is just simply the inverse tangent of omega over RC with a minus sign. Since the angle in the numerator is 0, and then we have an angle at the bottom, the minus sign appears for this when we complete this operation. Now we're going to do the Simulink demo to demonstrate that this is low pass filter. But let me note here that this equation describes a low pass filter, so because when you input radian frequency of 0, which is basically DC, the amplitude or magnitude of this is just 1. And if you put omega equals infinity, which is a high frequency, this is 0. So it passes the low frequencies by looking at these two extremes, and it rejects the high frequencies. Again, it passes the low and rejects the high. Now when omega is equal to 1 over RC, which we call the cutoff frequency, and in our example it will be 10 radians per second when we do the Simulink and Matlab demo, then the magnitude decreases, or the magnitude decreases by 3 dB, or goes to the 0.707 point. And that's a quick review. Okay, a quick review of what we did in our Simulink demo, and I'll add a couple things as well. Here we have our low pass filter, our sine wave input, and our scope, and we generated these from our library right here in Simulink. Now here this is configured. We can see that 10 is equal to 1 over RC, so our cutoff frequency is 10 radians per second. And our input, we're going to change it to 1 radians per second with an amplitude of 5. And we're going to see what the output of the scope is. So when you do that, you get a run, and we get an amplitude of 5, so it passes that. Let's say we change the amplitude to 10. So the amplitude should decrease to the 0.707 point. So 5 times 0.7 is 3.5. So run this one, and we see it decreased. Alright, and then we change the radian frequency to 100. It decreases even more. Now, just a quick note that I didn't show last time, edit, undo, is that we can, let me delete this, add another low pass filter in cascade, and we can even decrease the amplitude even more. So, paste right here. So this is now a second order low pass filter. Let me put that right here. And if you run this, and you see the amplitude is even more. So let me delete this and show you that it'll start to increase. and you see it, the amplitude increased even more. Let's change the input frequency to 10 radians and just see so you can recognize that, and then let's just add another low port to repeat what we did last time. Paste it, that right there, in there, and run it, and this should decrease even more, and you see it decreased. So adding more order filters will start to approach an ideal low-pass filter. So there's a trade-off between the complexity of the filter itself, the filter network, and how you want to approach the ideal case. So approaching the ideal case increases the complexity of the low-pass filter. So that concludes that demo. So let's just see the Matlab demo using the TF command and the Bode command. So now we're going to do a Matlab demo in terms of what we did in the Simulink. So here our numerator is 10. Our denominator is 1 and 10. And we're going to create a transfer function using the TF command. So our system is defined as a transfer function for our numerator and denominator. So this is our syntax. So the first parameter is the numerator, the second parameter here is the denominator. And so what we should get is our transfer function of 10s plus 10. Now we're going to draw a Bode plot so we can see the characteristics associated with this transfer function. So the command goes like this: Bode and our system definition, and that's all there is to it. And once you get a plot as a function of frequency, is like this. So we have a low pass filter. You could see the cutoff frequency is 10 radians per second, and that's our 0.707 point, and it rolls off at 20 dB per decade. We note here this is a phase plot, and at the cutoff frequency it has a phase shift of -45 degrees, and at higher frequencies it goes down to a maximum of -90 degrees, since this is a first order filter. And then when it passes the frequency, there's very little phase shift or delay at the pass span of the low pass filter. And that's all there is to it with this Bode diagram. Again, this roll off here is about 20 dB per decade. So you can see here's 20 dB, and that's 1 decade right here. So let's create a second order filter like what we did in our Simulink. So our denominator is we're going to use the poly command, which forms a polynomial coefficients. Alright, so we have roots of -10 as our inputs. So there's a second order, and should give us our coefficients as follows: as s squared 20s plus 100. So the numerator is 10 times 10, or 100, and our system is 2, second order, is a transfer function of numerator and denominator. And there we have it, s squared 20s plus 10, and the numerator is 100. And we'll do a Bode plot of sys2, and our figure is right here. And you could see the roll off is even more. It's still at 10 radians, but this time it goes at 40 dB per decade. And you can see at the cutoff frequency it's at 90 degrees, since this is a second order filter. And that concludes this demonstration using Matlab and the low pass filter.